Okay, I hope you can see my screen. That is the GeoGebra. What I want to show you is what will we discover, or what will we explore from maybe today and maybe next week, is something called the tangent plane. Okay, so if you are seeing this, so this is a surface. um, so it's ellipse, right? An ellipse, and this is the parabola, so it's elliptic paraboloid. And if you are looking at this line here, this line is actually a normal for this a plane here. Okay? You can see um, the color is a little bit blue green. I forgot the name of the color, um, but you can see the plane here. This is what we call the tangent plane. So when we are changing our, let's say we have a point, and we are changing our point, and let's say we are changing our A and B, we can also see that our tangent plane is also changing. Okay, so the tangent plane has two components. Um, so if you see here, it has component of x and it has component of y. So if you are looking at this uh, xy axis like that, it will has two components. So on the x and y. So if you are seeing this plane, we can cut this plane, and it has two lines. Okay, so the first line will be the the, the partial x, and the other line will be the partial y. I will show you later in the picture, but what it's supposed to be, it needs to be looking like this. Okay, so this line connecting, and it will be making something called a tangent plane, and this is what we are going to look for. So we are looking for partial derivatives, right? The partial derivatives, if you find on some point, you can combine those partial derivatives, become an equation of plane. Okay? So you need to also remember what equation of plane means and what is the equations. Okay, so that is what we are going to do. So let me uh, go back to here, and going back to our notes. Let me check. Okay, so this is supposed to be 14.4. Okay, that was supposed to be tangent plane and linear approximation. Okay, so like we have learned before, in 2 dimensions, we learned that we have a tangent line. And it was supposed to be approximating the function of x, right? If you remember that. And in 3 dimensions, like today's calculus, it's supposed to be figure out how to make a tangent plane from the surface. Okay? And by the end, we will approximate is two variable functions, or z. Okay, you want to write completely like that. Okay, and if you want to, let's say we are going to see in my drawing here, like you have seen before in the example on the tangent plane in the graphs. Okay, So if I have, let's say this is uh, my surface, okay, and maybe this is the point that we are going to look for, or the uh, any random point on x, y, okay, or maybe to be specific, maybe let's say x0 and y0, be specific on some value, and this will be the surface of z. Let's say this is function of xy, okay, and if we are cutting this, the surface become, we have two curve. Let's say this is curve uh, 2, curve 1, because I want to make 1 as x and 2 as in y. And then at this certain point here, it's supposed to be, oh sorry, it was supposed to be, let me redraw, it was supposed to be the same coordinate as this one. Let's say this. Okay, let's say that is the point. And this is C1, C2. Okay, now at this exact point here, okay, I want to draw, with respect to this C1, I have this line. And with respect to this C2, I have this line. Okay, so this will be the, as we mentioned in previous partial derivatives, this will be partial x, this will be partial y. Okay? And let me write here some notes here. So tangent plane will contain both lines. Okay. So what we are going to do is we choose, so let me write here. So we choose z lines that resulting when intersect with c with plane x equal x0 and y equal y0. This means this exact plane here. Okay, so imagine we have a plane here at this x equals 0. So we have plane like that. And this will be intersecting. And another plane may be in this y here. If I draw, maybe it will be messy, so I will leave it at your imagination. So imagine there will be a plane on this x0 and y0. And this point here is the intersection of the plane. Okay. So all this lines is basically, it came from a plane. Okay, plane from the x equal x0 and y equal y0. Okay. And how to make those plane? Let me write here. So the plane, we have the equations, as you know. That is our equation, equals 0. So x0, y0, and z0 is our point, right? And let's solve and let's simplify the form. So I will divide all by C, and then move out the A and B to the right side. So I will write the equations become Z minus C0, and the other will be going to the right side like this. Okay. And let's say this is some value A and some value B. Okay. And we can write this as A plus B. Okay. So, and then we can check, because we have plane x equals 0 and y equals 0, we can check when x equals 0, this is our plane here. I already gave you the answer actually. This is partial x and partial y. So let's just write down here. So when x is equal to x0, so this whole thing would become 0, right? So it will be b, and we can say that b is, or if you remember, this is practically or it's partial y, okay? And when y equal y0, this is practically this. Sorry. This is practically the partial x, okay? So we can have the conclusions. Let me write the conclusions here. The equation plane will be okay. I'm trying to simplify the equation on your textbook. I hope you get my point. Um, okay, that will be the equation of the plane. Okay. Okay. Maybe I can show you some example on how we can use it directly. So let's just use some direct example. For example, if you need to find the tangent plane, okay. So we can also write this z as function of x and y. Okay, so first, if this is statistic questions, then you just need to directly find the tangent plane and use the equations. Okay, so first, look at this point here. So this means this is x0, y0, and z0. Okay, that is based on this in equation plane of plane, right? So if you want to know what is this surface, this is elliptic paraboloid, right? Because when you have z equal to x squared, it's parabola. When you have z equal y squared, it's also parabola. But when you have 2x squared plus y squared equal a constant, it will be an ellipse, right? So it's elliptic paraboloid. But it doesn't really matter for the name now, because it isn't asking anything related to the name, right? So we are just focused on finding the partial x. Finding partial x from the equations, we need just to derive x and leave y as a constant, so it will be 0. And partial y will be 2y, and the other will be 0, right? And then plug into, this is plug into x equal 1, this is plug into y equal 1, right? So this will be 4, this will be 2. So it's not really complicated now. We can just write the z minus 3 and 4, x minus 1 plus 2, y minus 1, and you can solve the later. Okay. 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 Let me take to another page. Yeah, so I hope the tangent plane is not too very difficult. Let me check some of. Okay. Okay. Imagine. Let me draw first. Okay. Let me draw some surface. Imagine the surface is looking um, so it's like a sheet of paper, right? And if this is a surface, okay, and maybe I have a point maybe here, and let's say from those points I can create the tangent plane. Okay, so imagine you have this kind of surface, and what we are going to do is, let me write here, this is the tangent plane, this is the surface. Surface mean it can be any quadratic surface, as long as it is the function of at least two variables. Okay. Actually, I want to recreate what we did before. The z equal to x squared plus y squared. This is the surface, actually, but it's not really that accurate. And the point here should be 1, 1, 3. Okay, so what we are going to do, if we are taking zoom in at this point here, let's say this point P. So if we take zoom in, and I hope you can imagine what I'm going to do here. So if we are going to take the, so let's say, let me take. So let's say this is the area that I want to zoom in. Okay, so zoom. The more you are zooming in, you will see that your surface, let's say this is your surface, is getting approach as thin as the tangent. So when you're going to zoom in, zoom in, and zoom in, you will notice that the difference and you cannot tell the difference anymore when you are trying to zoom in and zoom in. So zoom in, this is zoom in again. So you will see that the tangent plane is actually as thin as the surface, the gap, okay, the gap. So it will be touching all the uh, the surface. Okay. So what does it mean? Which means that we can approximate, okay, a point. Okay. So this whole thing, this area here is uh, area near this coordinate. Okay. And it appears that this surface, okay, appears to coincide with tangent plane. So, okay, we can write, okay, the equation plane from before. Let's write this. Okay, let's write this equation from before. Okay, and these equations become good approximations of the surface when the point is near 1 1. Okay? Okay. For example, if you are looking for uh, this, it make let's say this, okay, and this. This is really good approach for this because it's nearby. It's nearby the point 1 1. Right? So we can also write this whole equation of plane here as L. So L is means that this is terms of linearization of the surface at 1 1. So linear approximation. Previously, you are approximating the only function of x, right? So now we can also use it to uh, approximate with a tangent plane. Okay. But you need to remember this is not always the case. This is only if, okay, it's near. Okay. Okay. So the conclusion from here, let me write for you so you can have a good visuals. Okay, let me write. So let me rewrite all the formula of the equation of plane. So recall this equation of plane. Okay, this is the tangent plane, and we call that our uh, if our point is AB, we have another point Z0. Okay, or you want to look going for X0, Y0, that's fine. It's same meaning. So if we are looking for linearization of the surface at point AB, we can write L is equal okay. I hope you don't be confused of this FAB. This is basically what the Z0 and this is C0. Okay. So this is Z. Okay. So this is Z. Before Z minus Z0, and we move C0 to the right, and we can write like this. So I think as long as you can understand how this formula works, okay, when you are doing these linearizations, it should be understandable. Okay, but it's only work if it's differentiable at this point. Of course, it should be continuous differentiable, right? So by definition, you can choose which one you need to, right? Okay. Um, because the first one here is just the introduction and explanation. So you can write from this one, I think. So if C equal f of x and y, then f is differentiable at point AB. And if we have delta z, if it can be expressed in form uh, this means partial x at AB and multiply with delta x plus partial y at AB multiplied with delta y plus there will be an epsilon 1 delta x plus epsilon 2 delta y. I need to know the epsilon means the value that really small. Okay, and here where the epsilon 1 and epsilon 2 approaching 0, okay, as the delta also approaching 0.0. So we have theorem that say if partial x, partial y exists near AB and continue at AB, then f is differentiable at AB. Okay, I hope you get the point. It's kind of complicated, but what does it really mean is this epsilon mean and the delta mean. You see when you are zoom in this tangent plane here, when you see from this side here, it has this amount of gap, right? And when you are zooming in, the gap becomes uh, getting closer, right? The gap is getting closer. That is, oh, sorry. So the gap is getting closer, and that is what we are talking about in epsilon here. So when the delta, meaning the so like I said before, if it is nearby, like this one, the delta is 0.1 or 0.01, right? So let's say it can be related to getting approach to zero, and we can ignore that, okay? And we can satisfying the linearizations, okay? So we need to have, okay, we need to have the point should be near the exact tangent plane locations. Okay? I hope you get the idea. Let me show you with the example. Show the surface is differentiable at 1 and 0, and then find its linearization. Then use it to approximate 1.1 and uh, it's should be 1.1 and uh, okay, and negative 0.1. Okay, first, if we plug in the coordinate 10 to here, so add 10, this will be 1 e, and then 10 it should be 0 here, so it should be 1. Okay, so the surface, the z is 1. But then we need to find how the linearizations work. So we need to find, let me write the full equation. And then we have partial x. And remember, if we have this x, okay, we have this is 1 and this is 2, right? So we have two components of x. So we need to do a product rule, right? So first is x differentiate is become 1, so e xy plus x, and then differentiation of with x and y, it become x y e xy, right? Hope you can get used to this form. Okay. Okay, that's the partial x. And partial y, we only have one y here, so we can just differentiate that part. It become x multiplied by x, so it's x squared, and then e with xy. And then we need to evaluate So before we going to linearization, we need to prove first that it is exists and continues. So evaluate at 1, 0. Okay. If you look at this will be 1 and 1, right? So it will be 1 also. So all is clear, all is exists, so both exist and continue at 1, 0. Okay. And then we can write the, let me move here, the linear it's z0. Let me write the formula first so that you uh, remember the formula. Okay, z0 means when we plug in 1 and 0 to our original equations. We have that here, it's equal 1, so we can write this 1 plus, let's just write fx first, and then this is x minus 1, and then y minus 0. Okay, and then partial x and partial y, it should be 0 here, sorry. It should be both are fx or partial x is 1, and partial y is also 1. So we can place in our equation here. So just, so we can solve this, and we have, and this is our linearization. So what linearization mean, we can use these equations to approximate, use to approximate this coordinate. Okay. Now, what we are going to do, we just plug in the coordinate that we want to approximate. So, or I will just write down the, so 1.1 minus 0.1, or it's approximately 1. Okay, is it true? Okay, you can also check with your calculator how good our approximations. Okay, so remember, this should be approximate, so it's not exact, so it's not equal, so it's approximate. That the difference. Okay, so if we want to look at the real value, we can plug in this. We can plug in this value into our original equation. So 1 e, and then 1.1, and then we multiply with negative 0.1. And if you have calculator on you, you can check the calculators. This should be equal 0 0.9854, right? Right. And if we compare with the our approximation is 1, it's, I think, okay, if we don't really care about how accuracy will be, I think it's quite near, right? It's quite near. It's near or approximate the value. Okay. 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 I hope you get it about the linearizations. Do you have any question? No? Um, Let me continue a little bit. Let me check how much we still have. Okay. Um, okay, I think we can still have one more sections. Okay, okay, just this thing. Okay, please wait a moment. I need to check the book, and later I will need to show you something. Okay. Okay, wait a moment. I need to stop the mirroring first. I will mirror one more time. Okay. Okay, I think I can move. I try to mirror. Okay, we go back here, and okay. Okay, the next sections is called the differentials. Oh, uh, what suppose differentials mean? Okay, let me recall uh, the calculus one. We have a curve, right? And we have, let's say, 2 point. Let's say a or maybe x0, and then this is x0 plus delta x. So if we approach this, let's say this PQ, and if Q is getting closer to P, we can have this tangent line, right? And this tangent line have two components. If you look here, right? So we can write the delta y. This is actual change. So imagine the tangent line is moving. So the delta y is from here, and okay, it's not from here. So it's actual change of y from x equal x0 to x equal x0 plus delta x. And delta x is, uh, wait, it should be delta dy. So dy is a small change, right? Small change in y when we are using the tangent line. So this was supposed to be this is the delta y, and if you are looking at the tangent line, this should be dy. Okay. When delta x really small, dy can be used to approximate delta y, right? So if we are imagine this delta x is as small, let's say, become really small, then it's similar to what we have done in calculus 1. So if we are looking, zoom in this point, and we are looking at this point here, let's say zoom, maybe the difference is really small. Maybe almost no gap, almost no gap, right? You see that, okay? Almost no gap. So that is what the dx means. So dx can be used to approximate the delta y. Oh, dy, sorry. So we can simply write the total. By the way, the differentials mean when we are saying any dx, dy, we are talking about differentials. Okay, if we are looking at this dx, dy. Okay. So the total differential the general equation is, it's actually quite similar with our linear approximation. So we have dz but all the delta we are changing with the dx or dy. Okay, and then we can also write in terms of the Leibniz notation. So this is the general equation. So this is what we call the differentials. Okay, and if we are observing at some point, let's say at AB, so at x equal a and y equal b, then our differentials, we can set up the delta. And our linear approximation will be is approaching okay. This is our z, this is our z0, and this is dz. Okay. Okay, so I hope you get the point. Okay. So this is what we got. At the end of the day, that is what we are going to have. Now, if you want to look into the visuals, I'm taking a picture before, and let's say this is the picture. Okay, let's see here. This is what the all the delta, the dx, dy, dz. Okay, so let's look at uh, the surface. Okay, so this is the surface. So this is the surface. Okay, and this is your AB. Okay, that's your AB. So this coordinate is A, B, and this is Z, right? The function of AB. And at this point, we have the tangent, right? This is our tangent, the tangent plane. And this is what we have learned this previously, right? This is Z minus Z0, and this is X0, if you remember, if you want to look, write down in terms of X0 and Y0. Okay. Now, if we set up a height difference between all of this, okay? The dz and the delta z, what is the difference? Okay, what is the difference? So delta z is the difference between, okay, if you look at this point here, we have a difference in delta x, right? Delta y, it's plus delta x plus delta y. And then the z will become different value because of delta x and delta y. And thus, this become the delta z, okay? And the difference with dz is the dz is the difference in the tangent plane. So we have the tangent plane here. And dz is the difference of the tangent plane on the point here. Okay, so this is the point here. So this will be the dz. Okay. And all the delta x and delta y will be approaching this dx. The value is, we consider small value there. And thus we can write all the terms into dx and dy for the delta. Okay, and that is why you can have this equation here. Okay, this is actually, you can still think this is a delta, right? But when you are doing the differentials, the d means it's the rate of change. Okay, you can think this as a rate of change. Okay, rate of change. Right. Okay. So let me give you an example on how we look into case or problems. Okay. Let me move into the other page. So if we look at the examples, okay, if we have these functions here, if we want to look for total differential, what does it mean? It means that we need to write an equations in which we need to set up dz, dx, and dy. That will be our differential equations. So we can set up, um, if you want to write this as in these terms, we can write dz becomes, we differentiate with partial x, right? So we can set up partial x and partial y if you want to divide by 2 and then combine together into one equation. So partial x become the just y squared, right? And then dx. Okay. and then plus, we use the partial y. We have 2xy dy. And this will be our differential equations. Okay. So whenever you heard differentials, maybe in your other lectures, the differentials mean any equation that have d inside, okay? Which means the rate of change, okay? The rate of change in x, in y, in z. Um, you will need this core concept into, I think, other lecture as well. I think in most of lectures they will use these differentials, especially if you want to have simulations or yeah, mostly simulations or any calculations that they are going to have an approximation inside, and it will have some uh, differentials for to approximate. Okay, you need to remember that. Okay, so this is the first one. The second one, if you want to approximate change in z, change change in z. Let's say from 0.5 and 1 to 0.503 1004. Yeah, let's do this. So we can write dz, and we can use the differential equations to approximate the change. So we can write this in terms of, this is the partial x. So we put 1, so x and y, right? So we put 1 squared, and then we put the difference, the delta. So this, or let's say this is x0, y0, this is x. So this will be x minus x0, or the difference between the point that we want to approach and the first initial point. Okay, so this will be 0.003 and plus 2, and then multiply with 1 and multiply with 0.5. And the difference for the second one is 0.004. So we can get 0.007, which means, okay, which means z will increase. Okay. If, for example, this becomes 0.998, it will be minus, right? Here will be minus. So sometimes it can be minus here, right? It doesn't always to be positive, but it may be a minus. Okay? This is our approximations. Okay, so this is not really correct here, so it should be approximate. Okay, if you want to look for the actual difference, we can use the difference with the original equations. Let's just let me write the original equation, xy squared, right? So x is this, and then y is 1.004 squared, right? And then minus the original 0.5 and 1 squared. If you take your calculator and try to calculate all of this, it will be 0.00705. This is real calculation. This is approximation using differentials. Okay, and if you check the exercise later, I will also upload the PDF file for your exercise. So you can check later. So let me write maybe here first. I hope to still remember that in calculus 1 we have related rates, right? So we are like we have the triangle problem. This is L, maybe this is dy, dx, and we need to maybe one is moving here, one is moving in there, and how is they are going to meet, and at what points, blah blah blah. Right? We need to connect all the rates that have in the informations, right? And actually, what we are doing now in calculus 2, the differentials, is precisely similar to what we are doing in related rates. So we need to connecting all the differentials, okay? All the rate actually. So it's actually quite similar to related rates. The difference is we are using the tangent plane linear approximations. Okay, okay, let me write the example. So dimension of a rectangular boxes are 75 centimeter, 60 centimeter, and 40 centimeter. So each measurement is correct within 0.2 centimeter. Use differentials to estimate largest possible um, error when the volume of the box is calculated. Okay, so the important thing here, we have the accuracy or the error. It should be around 0.2, the maximum error that it can have. Okay, and we have rectangular box. Let's say this is maybe X, Y, and Z, right? Um, okay, I think this is also related to the maximum value. Okay, the maximum value. Like you have area or you have volume, but before it's only f of x, right? And now in this calculus too, we have x, y. Sorry for this additional notes. Okay, so here we have x, y, z for the rectangle. So first we are going to do is find the formula. So we need just to have formula volume, which is the x, y, z. And then after that, we need to find the partial. So we need to find partial x. And we have now three variables. So partial y and partial z. And then we need to evaluate. We need to put into our dv. So the differential equation, it can have more than two variables, three, four, five. It can happen, but mostly it's either two or three, mostly in cases. So we can apply all this. Okay, plug in all the um, informations, and we can use this error as our dx, dy, dc, because they are not giving you any informations. Is there any difference in dx, dy, dc? If there's no difference, then we can assume all will be the same error, right? So we can choose that to use to replace our variables. So 60, 40, and then 0.2, 75, 40, 0.2, and plus 75, 60, 0.2. And we got it's actually this much amount. If you want to look for how many percentage, we can divide this whole dv with the original equations. If you look at it, is around 1.1%. So this is the amount that we are going to find. So this 1.1 is the error percentage. Error percentage of volume. Okay. If we have time, we can still have some exercise, but maybe next Monday. And maybe I will continue a little bit, just a little bit on the next sections, 14.5. Okay. Just a little intro of what we are going to work on. So this is the end of 14.4. So 14.4 is tangent plane and linear approximation. And linear approximation, we have differentials, okay. Maybe any questions first? Okay, if not, let me go to 14.5, a little bit intro. Okay. So 14.5, it's the chain rule. Let me just go review calculus 1, the chain rule, or maybe in chapter 10, the parametric, right? You still remember that? We have this, right? And in parametric, you want to know the dy dx is dy over dt divided by dx over dt, right? But we are finding this, or we develop this formula with our knowledge of chain rule, right? But now in our cases, we now have at least two variables like this, in which we can also um, input our parametric inside x and y like that. So we have composition z equal function of x t and y t. Okay, and because of this expressions, this is expresses z as a function of single variable, right? This is expressing t, right? This is also t. So the x having variable t, y also having variable t. So because of that two, we will have z will express variable t. Now, let me write the chain rule. So we can write dz over dt, and then partial x, okay, and then dx over dt plus partial y and dy over dt. So this is partial, this is partial. Okay, I hope you get the idea behind the chain rule. Okay. So when you have the, let me write, maybe move this to the bottom here. So when you have c equal the function of xt and yt, which means we treat them as usual. We find the partial x, we find the partial y, okay? But later, we need to multiply not with the x, but because it's x, it's having another variable with t, we need to multiply with dt. This is the same thing. We need to apply dy, like from what we have learned before. But because it's function of t in y, we need to apply dt. Okay, is that clear for you? Okay. So this is the chain rule. There are several sections um, in the chain rule, and but I will stop here for now, and so you let you know the just the basic first. Okay, we will continue on next Monday. Um, so I hope you have received the introduction message from the beginning of the course. So I will write some of them in the informations later and announce for all of you. So the important thing is the next week we may have small pop quiz. It's actually maybe just 10 to 15 minutes work, maybe just 3 questions or 4 maximum. You may open your notes or book. Depends on the questions, but mostly you can open your book. I just want to know how much you learn and how much you find out about the lecture so far. And this all quizzes will be accumulated into a score for your third quiz. Okay, for your third quiz. And for the last quiz we have, if you haven't resubmit your grade, please resubmit your grade so that I can know which one haven't been modified and have been modified, and I will fix the score for you. And again, I'm really sorry for the all the technical problems for this online lectures and exam. I hope we can learn together, as I also learning all these online structures, platforms. So I hope we can have good learning process. Okay. So any questions from you? If no, then you can leave the meeting if you want, or if you want to ask through the chat box, you can type in the chat box and asking any questions. That's fine. Okay, if there's no questions, so I will stop the recording, and you can leave the meeting if you want.